Imagine a star, a brilliant beacon shining in the vast emptiness of space. For millions of years it has burned with a steady, unwavering light, a cosmic lighthouse guiding us through the darkness. But even the most powerful stars are not eternal. Their lives, though measured in billions of years, are ultimately finite, a grand story written in the language of nuclear fusion and gravity. Now picture a true giant of the cosmos, a star many times more massive than our own sun. These colossal stars are rare, but their influence on the universe is profound. Their immense mass means they burn hotter and brighter, living fast and dying young compared to smaller stars like our sun. Deep within its core, the star is a raging furnace, fusing hydrogen atoms into helium in a process that releases unimaginable amounts of energy. This nuclear fusion is what powers the star, creating the light and heat that radiate across the cosmos. For billions of years this process continues, a delicate balance between the outward pressure of fusion and the inward pull of gravity. But all fires fade, the star's fuel runs low, and gravity begins to win. As the hydrogen in the core is exhausted, the star can no longer support itself against its own immense gravity. The core contracts, growing hotter and denser, while the outer layers begin to expand and cool. The star swells into a red supergiant, its outer layers ballooning outward to hundreds of times its original size. The core, meanwhile, collapses under its own weight, setting the stage for one of the most dramatic events in the universe. Suddenly, the star can no longer support the crushing weight of its own gravity. In a fraction of a second, the core collapses and rebounds, triggering a titanic explosion, a supernova. This explosion is so powerful that, for a brief moment, the dying star can outshine an entire galaxy. The supernova scatters the star's outer layers into space, seeding the cosmos with heavy elements like carbon, oxygen, and iron, the very building blocks of planets and of life itself. But the story doesn't end with the explosion. The core that remains is so dense, so massive that nothing can stop its collapse. It shrinks down to an infinitesimal point, creating one of the most mysterious objects in the universe, a black hole. A black hole is an object of such mass and density that its gravitational pull is inescapable. The very fabric of space and time is warped around it, creating a region where the normal rules of physics break down. Nothing, not even light, can escape once it crosses the event horizon, the ultimate point of no return. This boundary marks the edge of the black hole, beyond which all information is lost to the outside universe. The star's light is extinguished, leaving only its gravity, a silent ghost haunting the cosmos. Where once there was brilliance, now there is only darkness, a void so complete that it can only be detected by the way it bends the light of stars behind it. What we see is a perfect sphere of blackness, a region from which no information escapes. The event horizon is the ultimate cosmic veil, hiding whatever lies within from the rest of the universe. It warps space-time, bending starlight and pulling nearby matter into a superheated disk. This accretion disk swirls around the black hole, heating up as it spirals inward, sometimes reaching millions of degrees. This accretion disk glows fiercely in X-rays as material is torn apart, emitting powerful jets of energy that can be seen across the universe. These outbursts are among the brightest phenomena in the cosmos, revealing the presence of black holes even when the holes themselves remain invisible. The black hole itself remains unseen, its existence inferred by its influence on its cosmic neighborhood. Stars may orbit an invisible point, or clouds of gas may be drawn in and heated to extreme temperatures, all betraying the presence of this hidden monster. It is a testament to gravity's raw power, challenging our understanding of reality. Black holes push the boundaries of physics, forcing us to confront the limits of our knowledge and the mysteries that still lie hidden in the darkness between the stars. What lies at the heart of a black hole? This is one of the most profound mysteries in all of physics. As we venture deeper into the darkness, we leave behind the familiar universe and enter a realm where our current understanding of reality begins to unravel. The journey to the center of a black hole is not just a trip through space, but a voyage into the very limits of human knowledge. Einstein's general relativity describes gravity as a curvature of space-time, a fabric that bends and twists in the presence of mass and energy. Massive objects like stars and planets create gentle dips in this fabric, guiding the motion of everything around them. But black holes are different. They are the ultimate test of this theory, where the warping of space-time becomes so intense that not even light can escape. A black hole is the extreme expression of this idea, a bottomless well where curvature becomes infinite. The event horizon marks the point of no return, beyond which all paths lead inward, deeper and deeper toward the unknown. Here the very nature of space and time is stretched to its breaking point. At its center we find the singularity, a point of zero volume and infinite density. This is not just a place where matter is crushed out of existence, but where the very concepts of space and time themselves cease to have meaning. The singularity is a region where our mathematical descriptions of the universe simply stop working. Here, the laws of physics break down, and general relativity fails. The equations that have guided us so far can no longer predict what happens. The singularity is a boundary, a place where our scientific map ends and the unknown begins. The singularity is a cosmic crisis where relativity and quantum mechanics collide. On one hand, gravity tries to squeeze everything into an infinitely small point. On the other, quantum mechanics demands uncertainty and fluctuation. The result is a paradox that challenges the very foundations of physics. To understand it, we need a theory that unites them, a theory of quantum gravity. Only then can we hope to peer beyond the event horizon and truly comprehend what lies inside the singularity, at the heart of a black hole. What if the singularity is not the end? Loop quantum gravity suggests space-time is woven from indivisible loops. This leads to the Planck Star, where collapsing matter hits a fundamental limit. A quantum force halts the collapse, preventing a true singularity. The Planck Star is a cosmic spring, compressed but with physical size. It exists on the edge of reality, where classical notions of space and time blur. The Planck Star theory completes Einstein's relativity, showing what happens when gravity meets quantum reality. Planck density is the theoretical maximum density matter can achieve. Imagine compressing the Milky Way into a space no bigger than an atomic nucleus. At this density, quantum pressure counters gravity, holding the Planck Star in existence. The matter inside is a quantum fluid where distinctions between matter and energy blur. The collapsing star bounces, but from our perspective, this process takes billions of years. Time is relative, a river that speeds up or slows down with gravity. Near a black hole, time slows dramatically. A clock near the event horizon appears to stop to a distant observer. The Planck star's bounce happens quickly for the matter itself but takes eons from our view. Black holes might be Planck stars in slow motion, cosmic time bombs waiting to release their energy. Do Planck stars explode? As black holes evaporate, their event horizons shrink. When the horizon matches the Planck star's size, the cosmic spring releases. This explosion could produce bursts of energy like fast radio bursts, FRBs. FRBs might be the dying cries of ancient black holes, evidence of physics beyond Einstein. Telescopes hunt for these bursts, seeking to confirm that black holes are gateways to rebirth. Black holes, once thought to be the ultimate destroyers of the cosmos, are now being reimagined as powerful engines of creation. These mysterious objects, with their immense gravitational pull, do not simply consume everything in their path. Instead, they play a vital role in the cosmic cycle, transforming and recycling matter on a scale that is almost unimaginable. As we peer deeper into the universe, we begin to see black holes not as the end, but as gateways to new beginnings, portals through which the universe continually renews itself. Black holes recycle matter, holding onto it for eons before releasing it back into the cosmos as they slowly evaporate. Through a process known as Hawking radiation, they emit tiny particles, gradually losing mass over billions of years. This slow release of energy and matter means that black holes are not just cosmic endpoints, but also cosmic recyclers, returning the building blocks of stars and planets to the universe. In the far future, when the universe has grown cold and dark, the final act of black holes may be to light up the void. Planck star explosions, cataclysmic bursts that occur as black holes reach their end, could become the only sources of light in an otherwise empty cosmos, briefly illuminating the darkness with their energy. These powerful explosions might do more than just shine. They could trigger the birth of new stars and even entire galaxies. The energy released in these moments could compress clouds of gas and dust, sparking the formation of new celestial bodies and breathing life into regions of space that were once thought to be dead. Some scientists even propose that when a black hole collapses to its smallest possible size, a Planck star, it could rebound in a spectacular event. a cosmic bounce that might give rise to an entirely new universe. This idea suggests that every black hole could be a seed, holding the potential for a new reality to emerge. In fact, some theories suggest that our own Big Bang, the moment our universe began, might have been the result of such a rebound, a dramatic event inside a black hole from a previous universe. If true, this would mean that every ending is also a beginning, and that the cycle of creation and destruction is endless. The cosmos is filled with secrets, and black holes may be among its greatest mysteries. Yet, they also promise renewal, reminding us that even in the deepest darkness, there is always the possibility of a new beginning. Through their cycles of destruction and creation, black holes teach us that the universe is never truly finished. It is always evolving, always finding ways to begin again.